Dear listener, hello, and welcome to the Deep Sleep Science channel. As you settle in and allow your body to grow heavy and quiet, we're going to drift together into a softer side of the cosmos, where some of the most important structures and energies are completely invisible to any camera or telescope, yet gently shape everything we can see. For now, you don't need to understand every detail. You can simply listen as we wander through a universe built not only from starlight, but from quiet, hidden frameworks that cradle galaxies, guide light, and slowly steer the fate of space itself. Around most large galaxies, including our own Milky Way, there is thought to be an enormous halo of invisible mass extending far beyond the familiar disk of stars and gas. Astronomers do not see this halo shining in any color of light. Instead, they infer its presence because stars at the edges of galaxies orbit faster than visible matter alone can explain, and because light from background galaxies bends more than expected when it passes nearby. The simplest explanation is that each galaxy sits inside a roughly spherical cocoon of unseen dark matter, whose gravity holds stars in their wide orbits and boosts the overall mass far beyond what we can count in stars, gas, and dust. This invisible halo becomes a kind of silent scaffold, giving galaxies their weight and helping them stay bound together over billions of years, even though no telescope can ever photograph the halo itself. On the very largest scales, the universe's expansion is speeding up, and the agent responsible is called dark energy, a form of energy that seems to be built into space itself. Astronomers discovered this acceleration by studying the brightness and redshift of distant exploding stars, and by comparing those results with patterns seen in the cosmic microwave background and galaxy surveys, finding that distances grow faster than a universe filled with only matter would allow. Dark energy does not clump into objects, does not glow, and does not cast shadows. It appears as an almost uniform background that acts like a negative pressure, pushing space to expand ever more quickly. In this way, dark energy becomes a completely invisible property of space-time, not seen directly but inferred from the way the cosmic expansion curve bends away from what gravity alone would do. Some theories go further and suggest that this mysterious energy might not be perfectly constant in time, but instead could be driven by a slowly changing field often called quintessence. In these models, the field's energy density and pressure evolve as it moves through a landscape of possible values, causing subtle changes in how quickly the universe expands at different epochs. This field would not produce ordinary light or recognizable matter, and it would be spread very thinly throughout space, making it impossible to image directly. Instead, astronomers would look for its fingerprints in precise measurements of distances and the growth of structures over cosmic time, watching for tiny deviations from the behavior expected if dark energy were truly unchanging. If those deviations are ever clearly seen, they would point to an invisible, dynamic component quietly reshaping the expansion history of the cosmos. At the smallest scales, even what we call empty space is not truly empty, because quantum field theory says that fields in a vacuum constantly fluctuate around their lowest energy state. Pairs of particles and antiparticles flicker briefly into existence and then vanish again, too quickly and weakly to be directly observed by any telescope. We only know these vacuum fluctuations are real because they produce measurable effects, such as slight shifts in atomic energy levels and tiny forces between uncharged plates in laboratory experiments. In the early universe, these microscopic fluctuations were stretched to astronomical sizes by rapid expansion, planting the seeds of the density variations that later grew into galaxies and clusters. The original fluctuations themselves remain unseen, but their imprints form the delicate pattern of cosmic structure we observe today, making the restless quantum vacuum an invisible but fundamental influence on the shape of the universe. Closely related to this idea is the concept of zero-point energy, the residual energy that remains in a quantum field even at absolute zero temperature. When physicists try to calculate how much zero-point energy should be present, the naive result is enormously large, far exceeding what is allowed by observations of the universe's expansion. Yet cosmological measurements suggest a much smaller effective vacuum energy, similar in size to the dark energy density driving acceleration. Reconciling this huge mismatch is known as the cosmological constant problem, one of the deepest puzzles in modern physics. Telescopes cannot see zero-point energy directly because it does not manifest as a glowing substance. Instead, its influence shows up only in subtle laboratory experiments and in the global expansion rate of the universe, making it feel like a vast hidden energy reservoir whose true behavior remains largely unknown. Many models of the early universe include a brief period of extraordinarily rapid expansion called inflation, driven by a hypothetical field known as the inflaton. During this phase, the inflaton's energy dominated the universe, causing space itself to expand exponentially faster than the speed of light, smoothing out irregularities and stretching tiny quantum fluctuations to cosmic scales. When the inflaton field eventually decayed, it reheated the universe and led into the familiar hot Big Bang era. The inflation was never directly observable, and it likely no longer exists as a separate entity today. What remains are indirect signs encoded in the statistical patterns of the cosmic microwave background and in the large-scale clustering of matter. In this way, the inflaton is a historical but invisible participant, known only through the delicate signatures it left on radiation and structure, not through any light of its own. Shortly after the Big Bang, when the universe was less than a second old, neutrinos decoupled from the hot plasma and began streaming freely through space, forming what is called the cosmic neutrino background. These relic neutrinos are now extremely cold and low in energy, interacting so weakly with matter that no experiment has yet captured them directly. Their presence is strongly supported by the way they influence the formation of light elements during Big Bang nucleosynthesis and the fine details of cosmic microwave background fluctuations. If we could see them, we would find an almost uniform fog of ghostly particles passing through everything, including our own bodies, in vast numbers every second. For now, however, this neutrino sea remains a purely inferred cosmic bath, a silent record of the universe's first second that envelops us without ever announcing itself to our senses. If inflation occurred, it would not only have shaped the distribution of matter and light, but also produced a background of gravitational waves, ripples in space-time itself, that still linger today. These primordial waves would leave a distinctive pattern in the polarization of the cosmic microwave background, especially in the form of swirling B-mode polarization on certain angular scales. Experiments have searched for this signature, placing increasingly strict upper limits, but have not yet found a definitive detection. Unlike the sharp signals from individual black hole mergers, which we can hear as brief bursts in gravitational wave detectors, the inflationary background would be a permanent, random hum woven into space-time. It cannot be turned into a traditional image. Instead, it would reveal itself only through subtle statistical trends in radiation and timing data, offering a glimpse of quantum gravity processes in the universe's earliest moments. Over cosmic time, countless pairs of massive objects, such as supermassive black holes in merging galaxies, spiral together and emit gravitational waves. Many of these events are too distant or faint to be individually detected, but together they create an astrophysical gravitational wave background, a kind of persistent low-frequency chorus in space-time. Pulsar timing arrays search for this signal by monitoring the arrival times of pulses from rapidly spinning neutron stars. When a background is present, it produces correlated deviations across different pulsars. Even as evidence builds for such a common signal, it does not appear as bright spots on a sky map in the usual sense. It is experienced as tiny coordinated timing shifts. This makes the astrophysical gravitational wave background an invisible global vibration, perceived only by instruments that listen carefully to the regular ticking of cosmic clocks. Some theories predict that the early universe may also have formed extremely thin, high-energy defects called cosmic strings, which, if they exist, could radiate gravitational waves when they kink, cusp, or loop. Over time, the collective emission from many such events would add to a stochastic gravitational wave background, potentially overlapping with or distinguishable from other sources. No direct evidence for cosmic strings has been confirmed, and current observations mainly place limits on how strong their signatures can be. If a signal consistent with them were ever detected, the strings themselves would still remain dark, not seen as glowing filaments, but known only through their gravitational effects. In that sense, cosmic strings would be invisible threads stretched across the universe, revealed only by the ripples they send through space-time. Between the glow of the cosmic microwave background and the birth of the first stars, the universe experienced an era often called the Cosmic Dark Ages, when neutral hydrogen-filled space and very few luminous sources existed. During this time, the hydrogen could imprint a faint signature on the radio spectrum through its 21-centimeter transition, slightly altering the sky's average brightness temperature. Radio experiments try to measure this global signal and its fluctuations, but the imprint is extraordinarily weak and buried beneath strong foreground emissions from our own galaxy and other sources. Even if the signal is successfully extracted, it will not show individual clouds or structures, but rather a statistical map of how the average hydrogen temperature and density evolved. In this way, the hydrogen of the Dark Ages forms a nearly invisible fog, probed only through its collective influence on long-wavelength radio waves.
For many years, there was a mismatch between the amount of ordinary matter predicted by early universe physics and the amount actually seen in stars and gas inside galaxies and clusters. This led to the notion of missing baryons that had to be hiding somewhere beyond obvious luminous structures. Increasingly, observations and simulations suggest that much of this matter resides in diffuse gas spread along the cosmic web, especially in warm and hot filaments between galaxies that are too tenuous to glow brightly. One way to track this hidden material is through fast radio bursts, whose pulses are dispersed by free electrons. The degree of dispersion encodes how much ionized gas the signal has passed through. By analyzing many such events across the sky, astronomers are gradually confirming that a large fraction of ordinary matter lies in these nearly invisible intergalactic structures, quietly completing the inventory of what the universe is made of. A particularly important component of this hidden matter is the warm-hot intergalactic medium, gas heated to temperatures between roughly 100,000 and 10 million Kelvin, as it falls into the filaments and nodes of the cosmic web. This material is so diffuse that its X-ray and ultraviolet emission is extremely faint, making it hard to detect directly, even with sensitive space telescopes. Evidence for its presence comes mainly from narrow absorption lines of highly ionized elements in the spectra of bright background sources, indicating that the light has passed through hot, low-density gas. These lines reveal individual segments of filaments, but do not produce a continuous image of the network. As a result, the warm, hot intergalactic medium remains a largely unseen reservoir of matter, a hot, whisper-thin component that helps connect galaxies together, but rarely reveals itself as a glowing object in the night sky. Threading through this cosmic web of gas is another unseen component: large-scale magnetic fields that extend along filaments and into cluster regions. These fields are thought to originate from tiny seed fields, amplified over time by cosmic flows and turbulence, but they do not emit light on their own and are too weak to directly image. Instead, their presence is probed by studying how they affect the polarization of radio waves passing through magnetized plasma, rotating the polarization angle in a phenomenon called Faraday rotation. By measuring this effect along many different lines of sight, astronomers can infer approximate strengths and configurations of these vast fields. Even so, The resulting reconstructions are coarse and model-dependent, leaving the magnetic skeleton of the cosmic web as a largely invisible framework that guides charged particles and shapes plasmas without visibly announcing its presence. In an accelerating universe, there exists a cosmic event horizon, a distance beyond which events can never influence us, no matter how long we wait. This horizon is not a physical shell or barrier that glows. It is a boundary defined by the interplay between the expansion rate and the speed of light, marking the limit of regions whose light will ever reach us in the future. Galaxies currently inside this horizon may eventually drift beyond it. As space expands, their future signals forever cut off. We cannot point a telescope at the event horizon itself because it corresponds to a limit in space-time, not a visible surface. Yet it has deep implications for what parts of the universe we can ever observe or affect, making it a quietly profound feature of cosmic geometry that exists entirely outside the realm of direct imaging.
There is also a particle horizon, which marks the furthest distance from which light has had time to reach us since the Big Bang, and this defines the size of the observable universe at the present moment. Everything beyond that distance may well be filled with galaxies and structures, but their light has not yet arrived, so they are currently beyond our observational reach. The position of this horizon is calculated from cosmological models and measured parameters, like the expansion rate and matter content. But like the event horizon, it does not appear as a visible edge. The sky does not suddenly go dark at that boundary. Instead, we simply cannot receive information from space-time regions lying outside it. The particle horizon is thus an invisible limit to our view, reminding us that what we see of the universe is only a finite slice of a much larger whole. Another invisible property of the cosmos is its large-scale spatial curvature, a measure of whether space is overall flat, positively curved like the surface of a sphere, or negatively curved like a saddle. This curvature does not show up as obvious distortions in nearby shapes or measurements. Locally, the universe looks very close to Euclidean. Instead, curvature affects the relationships between distance, redshift, and apparent angular size when we compare objects across vast cosmic scales. By combining precise observations of the cosmic microwave background, galaxy clustering, and supernova distances, cosmologists find that the universe appears very close to spatially flat, with only tight limits on any small deviations. Because curvature is a global geometric property, no single photograph can reveal it. It emerges only from the careful statistical analysis of many observations spread across the sky and over billions of light years. Some theoretical frameworks that aim to unify gravity with quantum physics suggest that there may be more spatial dimensions than the three we directly experience. In these ideas, additional dimensions are usually compactified or otherwise hidden at scales far smaller than any current experiment or telescope can probe, so they do not show up as extra directions we can travel or point a camera toward. If such dimensions exist, their presence might be felt indirectly through subtle deviations from familiar gravitational behavior at very short distances, or through particular patterns in high-energy particle interactions or early universe cosmology. So far, no clear evidence for extra dimensions has been found, and all constraints are consistent with only three large spatial dimensions. Nevertheless, the possibility remains that the universe has a richer geometric structure than we can see, with additional directions folded away beyond the reach of direct observation. Many extensions of the standard model of particle physics propose very light, weakly interacting particles, such as axions or dark photons, which could form cosmic backgrounds somewhat analogous to the cosmic microwave background, but in a hidden sector. These particles would hardly interact with ordinary matter or light, making them invisible to conventional telescopes and difficult to detect in the laboratory. Specialized experiments search for them using resonant cavities, strong magnetic fields, and precision spectroscopy, hoping to convert tiny amounts of hidden sector energy into detectable photons
or shifts in known signals. So far, no definitive detection has been made, and the properties of any such backgrounds remain speculative. If they do exist, they would quietly fill space as an additional layer of dark radiation, affecting fields and interactions in ways that are subtle and, for now, out of sight.
Another intriguing possibility is that some fraction of dark matter might consist of primordial black holes, formed when rare, dense regions in the very early universe collapsed under their own gravity shortly after the Big Bang. These black holes could span a wide range of masses, from much smaller than the Sun to many times larger, and if they are not actively accreting gas, they emit almost no light. Surveys search for them by looking for microlensing events, where a compact object briefly magnifies a background star, and by examining gravitational wave data from black hole mergers and constraints from cosmic radiation. While certain mass ranges have been strongly limited, others remain allowed, keeping the idea of primordial black holes as dark matter candidates open. If they do make up part of the dark matter, they would form an unseen population of compact objects scattered throughout space, influencing dynamics and lensing, while remaining effectively invisible to direct imaging. Around most large galaxies, astronomers infer immense halos of dark matter extending well beyond the visible disks, forming spherical cocoons that cannot be photographed because they emit no light. These halos are discovered through the ways stars and gas move, where orbital speeds remain unexpectedly high far from galactic centers, indicating a great deal of unseen mass. Gravitational lensing confirms this by showing that background light bends more strongly than the visible matter alone can explain, revealing that galaxies sit cradled inside invisible envelopes that hold them together over cosmic time. In our own Milky Way, the dark matter halo dominates the mass budget outside the solar neighborhood, quietly shaping the motions of stars as they rise and fall through the galactic plane. Measurements of local stellar motions show more gravity than visible matter can account for, allowing scientists to estimate a local dark matter density that guides direct detection searches on Earth. Because the halo does not glow and barely interacts, its structure must be modeled statistically, revealing shapes that might be spherical, flattened, or triaxial, yet never directly seen. Simulations predict that inside these giant halos lie many smaller clumps called subhalos, composed entirely of dark matter and possibly lacking stars or gas altogether. These objects move through galactic space unseen, influencing stellar orbits and sculpting delicate gaps in tidal streams. Sometimes their gravitational pull slightly distorts background galaxies through lensing, hinting at entire populations of invisible structures scattered throughout halos like the Milky Way. As dwarf galaxies and clusters fall toward the Milky Way, they are stretched into long streams of stars, while their dark matter is also pulled into extended, unseen rivers. The stellar streams can be mapped faintly, but any associated dark streams pass completely unnoticed, except through their gravity. These hidden flows may change the local dark matter density near the Sun and leave small kinks in stellar streams, offering subtle clues to their presence. On the grandest scales, the universe arranges itself into a cosmic web of nodes, filaments, and voids, with dark matter forming the backbone. Galaxies trace these dense strands, but the dark scaffolding beneath remains unseen. Weak gravitational lensing and galaxy clustering reveal its ghostly shape only statistically, showing where mass collects even though nothing there emits light. Astronomers sometimes stack lensing data from many galaxy pairs to reconstruct average dark matter filaments between them, revealing faint bridges of mass that link systems. These filaments match what simulations predict, yet they never appear as luminous structures. Instead, they emerge as delicate patterns in bent light that quietly confirm a hidden cosmic architecture. Some galaxies may contain large reservoirs of hydrogen gas and dark matter, but very few stars, becoming nearly invisible to optical surveys. These dark galaxies, if they exist, might reveal themselves only through faint radio signals or unusual rotation curves. Whether stable systems or transient clouds, they represent the possibility of entire galaxies that evolve mostly in darkness. In dwarf galaxies, scientists debate whether dark matter piles steeply toward the center or flattens into broader cores. Telescopes see the stars, but only their motions reveal the underlying gravitational shape. The answer may depend on both dark matter physics and stellar feedback, leaving the true inner structure hidden and inferred rather than observed. Some models propose that dark matter particles may occasionally scatter off one another, allowing halos to evolve differently over time. These interactions cannot be seen directly, but astronomers examine colliding clusters, where gas and dark matter separate, to constrain what kind of self-interaction might occur. The interactions themselves remain invisible, known only through the shapes halos eventually take. If certain particles make up dark matter, they may sometimes annihilate or decay, producing faint backgrounds of gamma rays, electrons or neutrinos. Telescopes search for excess radiation, though distinguishing it from ordinary astrophysical sources is difficult. Even with a confirmed signal, the dark substance would not be visible, only the rare byproducts of events deep within a sea of unseen particles. Dark energy appears as a uniform property of space, driving the universe's accelerated expansion. It forms no objects, glows in no wavelength, and clumps nowhere. Instead, astronomers discover it by comparing distances, redshifts, and cosmic backgrounds, finding that space-time stretches faster than gravity alone predicts, revealing an invisible influence woven into the universe itself. Some theories imagine dark energy as a slowly changing field, gently evolving as it rolls across a cosmic landscape. Its presence would show up only through delicate shifts in the expansion history and growth of structures. Even if detected, it would remain unseen, existing everywhere as a diffuse, quiet background guiding cosmic evolution. Quantum physics suggests that even in a perfect vacuum, fields fluctuate, briefly creating virtual particle pairs before they vanish. These fluctuations cannot be watched directly, but they subtly affect atomic energy levels and cause tiny forces in laboratory plates. In the early universe, such microscopic tremors were stretched to cosmic scales, planting the first seeds of structure that later became galaxies. Zero-point energy, the residual energy present even at absolute zero, poses a deep puzzle because theoretical estimates vastly exceed what cosmology allows. We cannot observe this energy directly. It reveals itself only through minute laboratory effects and through the universe's expansion rate. Somehow, most of it seems cancelled or hidden, leaving one of physics' greatest unresolved mysteries. Inflationary theory describes a brief era when a hypothetical field caused space to expand exponentially fast, smoothing irregularities and amplifying tiny fluctuations. The inflationary itself has never been observed and no longer exists as a separate entity, yet its fingerprints remain etched into cosmic background radiation and large-scale structure. It is remembered only through the patterns it left behind. Soon after the Big Bang, relic neutrinos decoupled from matter and began flowing freely through space, forming a cold cosmic neutrino background. These particles pass through everything almost unnoticed, interacting too weakly to detect directly so far. Their existence is confirmed only by how they shaped early element formation and subtle patterns in the cosmic microwave background. Inflation should also have generated a faint, permanent background of gravitational waves humming through space-time. These waves cannot be turned into ordinary pictures. Instead, they reveal themselves as polarization patterns in ancient light or in precise timing of cosmic signals. So far, only limits have been set, keeping this invisible relic as an unproven but remarkable possibility. Over cosmic history, countless merging binaries and massive systems generate gravitational waves that blend into a background chorus. Pulsar timing arrays now find hints of this faint cosmic vibration. Yet even when confirmed, it will never appear as an image, only as tiny timing shifts spread across the sky. Some theories predict ultra-thin cosmic strings stretching across the universe, radiating gravitational waves when they kink or loop. No firm evidence has appeared, but experiments continue to listen for the subtle signatures they might produce. If ever revealed, they would still remain dark, recognized only by the ripples they imprint on space-time. Between the glow of the cosmic microwave background and the era of the first stars lies the Dark Ages, when neutral hydrogen filled space. Its faint 21-centimeter signal may one day map those ancient times statistically, though individual structures will remain invisible. Even with detection, astronomers would read only an averaged whisper from a universe without light. For years, cosmologists searched for missing ordinary matter expected from theory, but absent from galaxies. Fast radio bursts and other techniques now show that much of it hides in thin filaments between galaxies, in warm, diffuse gas. This matter forms vast, unseen reservoirs that complete the universe's accounting, yet rarely reveal themselves directly. In the earliest moments after the Big Bang, the universe was filled with a nearly uniform, hot plasma, yet tiny quantum fluctuations whispered through that smoothness. Inflation stretched those fluctuations to astronomical scales, gently imprinting slight differences in density that gravity would later amplify. These seeds were invisible at the time, lingering only as faint pressure variations in the primordial plasma. Over billions of years, they quietly guided matter into galaxies, clusters, and cosmic structures, showing how something so subtle and unseen could slowly shape the entire architecture of the universe. As the expanding universe cooled, protons and electrons combined into neutral hydrogen during a period called recombination. The fog of scattering electrons cleared, allowing radiation to travel freely, creating the cosmic microwave background we observe today. Yet the hydrogen itself remained largely invisible, forming vast dark regions without stars. In these quiet expanses, gravity continued to work slowly, letting diffuse gas collect into the first dense clouds that would eventually collapse and ignite. The very first stars formed deep inside these dark halos of invisible matter, collapsing from pristine hydrogen and helium with no heavier elements to help them cool. These stars were likely enormous, burning quickly and violently, flooding space with intense ultraviolet light that began to ionize the surrounding gas. Though their light has long since faded, and no telescope can see them directly, their influence transformed the universe, ending the cosmic dark ages and beginning a new era filled with structure and heat. When those massive first stars exploded as supernovae, they scattered heavier elements into surrounding space, enriching it for future generations of stars and planets. The shockwaves stirred invisible gas, driving turbulent motions that mixed the new elements far beyond the original stars' locations. These explosions also altered the dynamics of nearby clouds, encouraging some regions to collapse while dispersing others. What we now observe in stars and planets across space carries the quiet signatures of these ancient, unseen enrichment cycles. Young galaxies assembled through repeated mergers and gradual accretion, growing from small irregular clumps into complex rotating systems. Much of this assembly unfolded within deep wells of dark matter gravity, guiding luminous material along predetermined paths. Collisions heated gas, triggered bursts of star formation, and rearranged orbits, yet much of the true mass involved remained completely dark. The galaxies we see today are final, glowing outlines built atop this invisible history of merging structures. As galaxies grew, some developed supermassive black holes at their centers, whose gravity and outflows influenced surrounding gas. Jets and winds from active nuclei could heat or expel material, suppressing further star formation and changing the evolutionary trajectory of entire galaxies. The black holes themselves remained dark, revealing their presence only through surrounding matter. Over time, these invisible engines quietly sculpted galactic growth without ever appearing as luminous objects. Clusters of galaxies formed at the nodes where cosmic filaments intersected. gradually drawing in matter from enormous regions of space. As gas fell inward, it was heated to extreme temperatures, creating a hot plasma that glowed in X-rays, while the bulk of the binding mass remained in vast clouds of dark matter. Weak gravitational lensing maps show their shapes, but never reveal the dark component directly. These clusters became the largest gravitationally bound structures in the universe, assembled through long, unseen processes, driven primarily by invisible matter. As more stars lived and died, supernova explosions continued enriching galaxies with heavier elements, building the cosmic chemical cycle. Planet-forming materials emerged only after many generations of stellar life, showing that rocky worlds depend on ancient evolutionary chains stretching across billions of years. Most of this transformation occurs in diffuse gas clouds that appear empty at visual wavelengths, yet within them fundamental changes quietly unfold. The growth of cosmic complexity is therefore rooted in environments that remain largely unseen. At certain stages, galaxies undergo quiet quenching, where their star formation slows dramatically. Sometimes this occurs when fuel is exhausted. Other times, environmental effects, heating or feedback lift gas out of dense star-forming regions. Much of the critical action takes place in warm, low-density halos that are faint and difficult to detect. Over long timescales, invisible processes gradually shift galaxies from vibrant star factories into calmer, more passive systems. Massive galaxies continue to merge, sometimes violently, altering orbits, mixing stars and triggering transient bursts of light that fade over cosmic time. After the visible fireworks end, the merged system settles into a new structure, its long-term dynamics governed yet again by the underlying invisible halo. The final galaxy shows little sign of the intricate gravitational dances that produced it. What remains is a deceptively calm object, hiding a complex evolutionary story written mostly in gravity. Even within galaxies, stars migrate gradually across the disk, moving inward and outward, under the influence of spiral waves and bars. This migration is slow, often unfolding over billions of years, and leaves no obvious visual trail. Yet it subtly changes where stars of different ages and compositions end up, blending stellar populations throughout the disk. The quiet reshuffling is an invisible contributor to galactic evolution, altering patterns without creating noticeable landmarks. In the halos around galaxies, relic streams from past mergers slowly disperse. Stars that once traveled together gradually stretch, thin, and fade into the background. Their associated dark matter streams disperse even more thoroughly, leaving only delicate gravitational imprints behind. Over time, the memory of these ancient accretion events becomes nearly impossible to see, surviving mainly in models and faint dynamical signatures. At larger scales, voids expand as matter flows outward along filaments. These vast regions grow increasingly empty, yet they influence cosmic structure by stretching nearby filaments and clusters. Their interiors contain tenuous gas and extremely low-density dark matter, both essentially invisible. Despite appearing as nothing, voids actively participate in the slow evolution of the cosmic web. As cosmic time advances, the accelerating expansion driven by dark energy gradually isolates structures from one another. Galaxies not gravitationally bound drift beyond each other's reach, leaving island universes surrounded by darkness. This separation happens smoothly and silently, without visible boundaries appearing in the sky. The future universe quietly evolves toward increasing isolation, guided by a force that no telescope can see. Some theoretical models suggest that dark matter itself may evolve differently, depending on its microscopic nature, potentially influencing how halos grow and how galaxies assemble. Whether through self-interactions, warm properties, or alternative behaviors, much of this evolution would leave only subtle traces in large-scale structure. Observers would never see the particles directly, only the consequences in galaxy distributions. Thus, Even fundamental cosmic ingredients may undergo histories hidden beneath observable light. Chemical enrichment of intergalactic gas continues as galaxies blow winds into surrounding space. Metals disperse through faint filaments, mixing into vast reservoirs of material that future galaxies may reuse. Observations often detect these elements only as absorption features against distant quasars. The gradual spread of heavy elements becomes an invisible tapestry woven between galaxies across cosmic epochs. Star formation itself follows a slow evolutionary arc. Early star formation rates were intense, gradually declining as gas supplies thinned and heating mechanisms changed. The cosmic star formation history is reconstructed statistically, since much of the process took place in dusty, faint environments. What we know about this grand rise and fall comes from indirect signals, not from any direct visual record of the full process. Planetary systems evolve as well, with debris disks clearing, worlds migrating, and remnants scattering over time. Many such transitions occur long after the bright early stages have faded. Observers see only traces, dust belts, comet reservoirs, or unusual orbits. The true histories of planetary systems are largely invisible chronologies written in gravitational motion. Even at the scale of entire universes, some cosmological models describe long-term fates we cannot yet observe, endless expansion, slow freezing, or other possibilities shaped by components we barely understand. These outcomes depend on parameters that remain uncertain, tied to unseen forms of energy and matter. The universe's future silently unfolds according to laws we are still piecing together. In this way, cosmic evolution remains not only grand and beautiful, but also profoundly hidden from direct view. Inside bright nebulae, hot young stars carve out glowing regions of ionized hydrogen, yet the true boundary where neutral gas becomes ionized is so thin and delicate that no telescope can resolve it. This invisible layer, the ionization front, is where heating balances cooling, where radiation pressure pushes, and where gas pressure pushes back. Simulations show that these fronts ripple, fold, and fluctuate, with tiny instabilities shaping how the front moves through the cloud. Even though images show large luminous bubbles, the actual transition surface remains hidden, a mathematically reconstructed boundary quietly deciding how starlight changes the environments around newborn stars. Deep within dense molecular clouds, where starlight barely reaches, cosmic rays drift silently through the gas and act as the primary source of ionization. These high-energy particles cannot be tracked individually, but they strike atoms and molecules, triggering long chemical chains that gradually build complex organic compounds. Observers detect only the resulting molecules through radio emission, not the original cosmic ray hits that set everything in motion. By comparing the observed chemistry to models, astronomers infer the underlying cosmic ray flux, recognizing it as an invisible environmental control knob, shaping how clouds cool, collapse, and ultimately form stars. In the hot outer atmospheres of stars, magnetic fields twist, stretch, and eventually snap and reconnect, releasing vast amounts of stored energy. The thin sheets where reconnection truly happens are incredibly small, incredibly hot, and fundamentally beyond direct imaging. We see bright loops, bursts, and flares, but the actual reconnection sites exist only as inferred structures within the magnetic field itself. Their behavior must be pieced together from models, indirect signatures, and laboratory plasmas, making them crucial but unseen triggers of stellar storms. Far from the Sun, its rotating magnetic field creates a gigantic, spiraling surface that winds outward through the solar system, the heliospheric current sheet. This wavering boundary marks where the magnetic polarity reverses, yet it emits no light and cannot be photographed. Spacecraft feel it only as sudden flips in magnetic direction and subtle changes in plasma. Over the solar cycle, the sheet becomes more warped and then smoother again, influencing how energetic particles travel through the heliosphere. Global models stitch measurements together to reveal its shape, turning this invisible surface into a reconstructed map that extends beyond the orbit of Pluto. Encircling Earth are belts of trapped radiation formed by charged particles captured by the planet's magnetic field. These regions do not glow in visible light and are known mainly through particle detectors carried by satellites. Their shape and intensity change as geomagnetic storms compress and energize different populations of electrons and ions. Understanding these unseen belts is essential because they pose hazards to spacecraft and astronauts, and their behavior reflects how energy flows through near-Earth space. Over time, long-term monitoring has slowly transformed them from mysterious zones into structured, though still invisible regions. Closer to Earth lies the plasmasphere, a torus of relatively cool, dense plasma that co-rotates with the planet's magnetic field. Its outer edge, called the plasma pores, marks a transition between different plasma populations, yet remains transparent to ordinary light. We know it exists because spacecraft measure electron densities and because radio waves behave differently when passing through it. During geomagnetic disturbances, tongues of plasma peel away, extending outward and interacting with the outer magnetosphere. These soft, unseen flows guide how energy is transported and dissipated around our planet.
In cosmic voids, which are some of the most underdense regions in the universe, gravity still shapes gentle potential wells that subtly influence galaxy motions and passing light. As photons cross these regions, they gain and lose tiny amounts of energy, creating minute temperature variations in the cosmic microwave background. These changes cannot be seen directly, but appear statistically when scientists correlate maps of galaxies with maps of background radiation. Voids therefore behave like barely noticeable hills and valleys, carved into space-time, invisible yet measurable through their effects. When cosmic microwave background photons travel through evolving gravitational landscapes, they experience the integrated Sachs-Wolf and Rees-Syama effects, gaining or losing energy, depending on how the potential wells change with time. These changes are impossibly small on any single image, but they accumulate across the entire sky. Researchers detect them by comparing galaxy surveys with CMB maps and discovering subtle correlations. What is being measured is not an object, but a process, time-varying gravity leaving a whisper of influence on ancient light. In regions surrounding black holes, dark matter may become compressed into steep spikes, where its density rises dramatically toward the event horizon. These structures consist entirely of invisible matter and produce no light on their own. If dark matter annihilates or decays, the spikes could generate faint signals of radiation detectable by sensitive telescopes, but the spike itself would remain unseen. Its existence must be inferred from indirect glow and gravitational modeling, making it a theoretical structure wrapped around one of the universe's darkest objects. Primordial density fluctuations seeded during inflation still exist as mathematical patterns woven into space-time. They cannot be observed individually. Instead, scientists study their statistical fingerprints imprinted on the cosmic microwave background and the distribution of galaxies. Properties such as near-scale invariance and Gaussian behavior help reveal how these invisible ripples behaved. Any deviations might hint at new physics, but the fluctuations themselves remain forever hidden, detected only through their collective imprint across billions of light-years. Inside the faintest dwarf galaxies, the shape of the dark matter distribution at the center, whether sharply peaked or broadly spread, remains a subject of deep investigation. Observers track stellar motions and gas dynamics to reconstruct what cannot be seen directly. These structures carry clues about both dark matter physics and the ways supernova feedback may reshape galaxies from within. Although theories differ, the true gravitational landscape remains a silent, invisible feature beneath the stars. Some models suggest that dark matter particles can occasionally scatter off each other, allowing halos to evolve differently than in standard scenarios. Astronomers test this possibility by examining galaxy clusters where visible gas separates from dark matter during collisions. By comparing their motions and structures, scientists can set limits on how strong such interactions might be. The processes themselves remain hidden, taking place in a realm that does not emit light, but their cumulative influence leaves faint signatures across cosmic structure.
If dark matter consists of annihilating or decaying particles, then the cosmos may hold a diffuse background of radiation created by these rare events. Telescopes sometimes pick up unexplained signals, and researchers carefully compare them to known astrophysical sources. Even if the signal truly originates from dark matter, what we see is not the dark matter itself, but the faint aftermath of invisible interactions. The underlying particle sea remains concealed, revealed only through delicate clues. The faintest dwarf galaxies predicted by theory may remain largely undiscovered because their surface brightness is too low to detect. They contain stars and dark matter, yet appear almost transparent against the cosmic background. Lensing signals and stellar motion sometimes hint at their presence. These hidden companions quietly contribute to galaxy evolution, shaping gravitational environments while remaining barely, if ever, visible. Within the disk of the Milky Way, some theories predict compact clumps of cold dark matter drifting quietly through space. With no stars and no gas, they reveal themselves only by lensing or by tiny disturbances in stellar streams. So far they remain hypothetical, but if they exist, they would influence structure formation and possibly even planetary systems. Their presence would remind us that invisible architecture can exist inside regions that otherwise look familiar and bright. Certain theories propose ultralight dark matter behaving like a quantum wave across entire galaxies. Instead of acting like individual particles, it forms wave-like interference patterns and central solitonic cores. Telescopes cannot see the waves themselves, only the smoothed-out density they produce. If confirmed, this would mean that vast, unseen quantum patterns are quietly sculpting galaxies on cosmic scales. The cosmic neutrino background should carry its own subtle anisotropies, tiny variations in direction and temperature, echoing early universe fluctuations. These differences are far beyond our ability to map directly, because neutrinos interact incredibly weakly and at extremely low energies. Still, their influence appears in how structures grow and in small details of the microwave background spectrum. The pattern exists, even though we can sense it only through indirect fingerprints. If inflation did not last forever, then regions beyond our observable universe may preserve traces of pre-inflationary structure. These zones are forever beyond our horizon, meaning no signal from them can ever reach us. Theorists sometimes speculate that anomalies in the cosmic microwave background might hint at these earlier conditions, but such ideas remain difficult to test. Whatever lies outside our observable boundary remains permanently invisible, forming a silent continuation of space we can never directly explore. Across the cosmic web, occasional mini-clusters and compact concentrations of dark matter may roam as quiet gravitational perturbers. They contain no stars, and they do not shine, but their gravity can subtly disturb stellar motions or planetary systems that pass nearby. Detecting them requires patient observation and careful modeling, because they leave only delicate traces. If they exist in large numbers, they add yet another hidden layer to the universe's unseen structure. Inside dense molecular clouds, dust grains accumulate electric charges through collisions, radiation, and interactions with cosmic rays, turning them into tiny charged particles drifting through gas. These charges change how grains stick, align, and settle, affecting the chemistry, the temperature balance, and even how the cloud collapses into stars. We cannot see individual charges, nor can any telescope capture the intricate patterns of electrostatic behavior unfolding grain by grain. Instead, scientists infer the charging from models, laboratory plasma experiments, and its subtle influence on gas dynamics, recognizing that invisible electrostatic effects silently guide how matter clumps together in the dark. Around young stars, ionization fronts create thin transition layers where cold neutral gas suddenly becomes hot, ionized plasma under the pressure of intense ultraviolet light. The true boundary is razor-thin, shaped by heating, cooling, gas pressure and radiation pressure, all working together. Observations reveal bright surrounding nebulae, but the delicate internal structures of the front itself remain hidden. Simulations show curling, rippling and instability patterns that control how these bubbles expand, either encouraging new stars to form or suppressing their birth in nearby clouds. Within molecular clouds, cosmic rays quietly ionize hydrogen and other molecules, triggering chemical chains that create complex organic species. The cosmic rays themselves never appear in telescope images, only their chemical aftermath is visible through faint emission lines. The rate of ionization controls how magnetic fields bind to gas, how easily clouds collapse, and how molecules grow or decay. By comparing observations with chemical models, astronomers reconstruct the invisible cosmic ray environment, realizing it functions like a hidden regulator of star-forming chemistry. In stellar coronae, magnetic fields twist and fold until they reconnect, releasing energy that heats plasma, drives eruptions, and accelerates particles into space. Telescopes see bright loops and flaring light, but the true reconnection layers, thin, hot, dynamic, are far too small to resolve. Their shape, motion, and behavior exist mostly as inferred mathematical surfaces within the field. Scientists study plasma experiments and numerical models to piece together what cannot be seen directly, knowing that these unseen sheets govern the most violent episodes in stellar atmospheres. The heliospheric current sheet extends through the solar system as a vast spiraling boundary where the sun's magnetic polarity flips from one side to the other. It does not glow, reflect, or scatter light. Instead, spacecraft detect it only when they cross it, noticing sudden reversals in magnetic direction and slight changes in plasma properties. Its shape shifts with the solar cycle, becoming warped and complex near solar maximum. By combining in situ measurements with maps of the sun's magnetic field, researchers reconstruct an enormous invisible surface stretching beyond the outer planets. Earth is surrounded by radiation belts filled with energetic electrons and ions trapped by the magnetic field. These belts are dangerous to spacecraft and astronauts, yet they are invisible in ordinary light. We know their shapes and changes only from particle detectors aboard satellites, revealing how geomagnetic storms inject, accelerate, and sometimes strip particles away. Their structure is dynamic, flexing with solar activity in ways that quietly govern space weather around our planet, forming unseen but powerful regions of radiation. Inside the radiation belts lies the plasmasphere, a cool, dense plasma region that rotates with Earth like a gentle halo. It cannot be captured by cameras. Instead, it reveals itself through radio wave behavior and spacecraft density measurements. During geomagnetic storms, parts of the plasmasphere peel away into long plumes that stretch sunward. These unseen flows influence how energy moves into the outer magnetosphere, shaping storms, auroras, and long-term space environment conditions in subtle, hidden ways. Around gas giants, magnetospheres form huge protective bubbles where planetary magnetic fields deflect solar wind. Inside these magnetospheres, charged particles travel along invisible field lines, sometimes precipitating into atmospheres to form auroras. The global magnetic structures themselves cannot be seen directly. They are reconstructed from spacecraft tracks and radio measurements. The intricate currents, trapped particles, and field topology become a vast, unseen system guiding how planets interact with the solar wind. When stars form in disks of gas and dust, turbulence, radiation, and magnetic fields interact in ways that control where matter flows and where planets may eventually form. The disk's outer layers may be ionized, while the midplane remains mostly neutral, creating zones where gas couples differently to fields. Many of the most important instabilities unfold at scales far too small for telescopes to resolve. Within interstellar gas clouds, turbulence behaves like a cosmic weather system, cascading from large scales down to small eddies and shocks. This turbulent structure shapes where clouds fragment and where stars eventually form. Yet most of the turbulence is invisible. Astronomers deduce it from velocity spreads in spectral lines and from simulations that match statistical patterns. The unseen swirling motions determine how quickly clouds collapse, how heat spreads, and how star formation begins or stalls. Magnetic fields thread through interstellar space, guiding cosmic rays, affecting cloud collapses, and shaping shockwaves created by supernovae. Although we cannot see the fields themselves, polarization measurements reveal their orientations, and Zeeman splitting helps estimate their strengths. Their lines bend and twist, providing gentle restraints on gas motion. Without being visible, they quietly organize much of the structure and evolution of interstellar matter. Shockwaves propagate through space whenever fast material slams into slower gas, heating, compressing, and ionizing it. We may see glowing shells or radiation produced after shocks pass, but the shock front itself is vanishingly thin and invisible. These fronts regulate star-forming clouds, accelerate cosmic rays, and shape supernova remnants. Feedback loops operate throughout galaxies as stars form, explode, and stir surrounding gas. Winds, radiation, and supernovae heat and expel material, regulating how quickly new stars can appear. The large-scale glow of galaxies hides this fine-scale interplay that determines long-term evolution. Much of the regulation happens in low-density regions, too faint to see directly, where invisible pressure, turbulence, and energy transport quietly shape the fate of entire systems. Even inside planetary interiors, convection and rotation produce hidden magnetic dynamos that generate global magnetic fields. We cannot see the swirling molten motions deep below the surface, but satellites detect the resulting fields in space. These invisible internal processes protect atmospheres, deflect radiation, and influence habitability. They continue for billions of years, unseen, as slow planetary heartbeats shaping the environments that worlds present to space. In hot plasmas, electrons and ions sometimes travel great distances between collisions, meaning that temperature, pressure, and density do not behave like simple gases. Instead, microscopic interactions create anisotropies and instabilities that ripple outward to larger scales. Observations reveal broad consequences, like filamentary structures and unexpected heat flows, without ever exposing the underlying particle trajectories. The real activity happens at scales impossibly small to image, but completely essential to the behavior of clusters, stars, and nebulae. When cosmic rays strike atoms, they create secondary particles that cascade into showers, producing radio signals, flashes of light, and chemical changes. Yet the original cosmic ray is often just a single high-energy particle traveling alone across great distances. Instruments register its arrival as a fleeting event, while the journey itself remains unseen. Quantum tunneling allows particles to slip through barriers they classically should not cross. In stars, this phenomenon lets protons fuse at temperatures lower than otherwise expected. On microscopic scales, it becomes an essential ingredient in nuclear reactions, chemical behavior, and even some biological processes. But tunneling cannot be photographed. It is known only through outcomes that defy classical predictions. In protoplanetary disks, dust grains slowly grow through sticking collisions, forming aggregates that become pebbles, then larger bodies. Each adhesion event is fragile, governed by van der Waals forces and surface chemistry. Observations capture only the broad outcome: dust settling, rings forming, gaps appearing. The delicate first steps toward building planets occur invisibly, grain by grain, far below any practical resolution. At the quantum level, entanglement links particles so that measurements on one instantly affect the state of another, even when separated by great distances. Astronomers study entanglement indirectly in radiation fields and theoretical cosmology, suspecting that early universe fluctuations originated from quantum connections stretched to cosmic scales. The entanglement itself cannot be pictured or isolated. It exists as a deep, unseen structure beneath the classical world we observe. Even the vacuum itself may contain fluctuating fields whose average energy density influences cosmic expansion. These virtual excitations appear and vanish in unimaginably short intervals, never forming anything a telescope could detect. Their effects show up in particle physics experiments and in cosmological parameters instead. Beneath the visible universe lies a restless quantum background we cannot directly perceive, yet it shapes reality at both microscopic and cosmic scales. Astronomers cannot photograph dark matter, so they instead map its presence through gravitational lensing, measuring how light from distant galaxies bends as it travels past massive structures. The more the light is distorted, the more invisible mass must be there, creating delicate shear patterns across the sky. Huge surveys collect millions of galaxy shapes and stack them statistically, revealing a ghostly mass distribution with filaments, clusters, and voids. We never see the dark matter itself, only the way it nudges light along bent paths, quietly revealing where mass hides. In galaxy clusters, the hot X-ray emitting gas often sits displaced from the peak of gravitational mass, as seen when clusters collide. By combining X-ray images with gravitational lensing maps, scientists can separate where normal matter lies from where the dominant unseen matter resides. Famous examples show the gas slowed by drag, while dark matter sails through almost unaffected, offering some of the clearest evidence that something invisible contributes most of the mass. The images show familiar structures, but the most important component exists only as a gravitational signature layered beneath the light. Microwave background experiments observe subtle temperature and polarization variations across the sky, not by seeing distant objects directly, but by recording relic radiation from the early universe. Precision instruments measure differences only millionths of a degree above absolute zero, building maps that encode the primordial density field. From these tiny variations, cosmologists infer the composition, age, curvature, and history of cosmic expansion. What the detectors capture is not scenery, but ancient information carried in a faint, omnipresent glow. Radio telescopes listening for the 21-centimeter signal from neutral hydrogen do not see individual clouds as images. Instead, they detect average brightness over patches of sky and frequency slices corresponding to different cosmic times. Foregrounds from our own galaxy overwhelm the desired signal, requiring careful subtraction and statistical reconstruction. If successful, the result is not a picture, but a timeline of cosmic dawn and the Dark Ages, extracted from an almost imperceptible whisper in the radio background. Pulsar timing arrays use millisecond pulsars as cosmic clocks, monitoring their radio pulses for years to detect tiny deviations caused by gravitational waves stretching space-time. No telescope sees the waves passing through space. Instruments simply notice that pulses arrive a little early or a little late. By comparing many pulsars across the sky, scientists look for correlated timing patterns that reveal a background hum of distant mergers. The discovery comes not from direct sight, but from exquisitely precise listening. Direct dark matter experiments deep underground search for rare particle collisions inside shielded detectors. Scientists wait for faint flashes, ionization tracks or phonon vibrations that might reveal a single interaction in enormous volumes of crystal, liquid xenon, or supercooled material. Most of the time, nothing happens except background noise carefully filtered away. If a true signal appears, it represents an unseen particle entering the detector, brushing against atoms, and vanishing, detected only through the smallest possible trace left behind. Neutrino observatories fill vast tanks of water, ice or other materials and watch for the rare moments when a neutrino interacts. When it does, faint cones of light, called Cherenkov radiation, spread through the detector, allowing scientists to reconstruct direction and energy. The original neutrino remains invisible, only the interaction products betray its passage. From these few events, scientists learn about stellar interiors, supernovae, the Sun, and even distant cosmic accelerators. Gamma-ray telescopes study the highest energy photons, not by capturing them directly in images as optical telescopes do, but by detecting their collisions with detectors and secondary particle showers. On the ground, atmospheric Cherenkov telescopes see brief blue flashes created when gamma rays strike Earth's atmosphere. Reconstruction software then infers where the photon came from and how energetic it was. The sky, at these energies, is pieced together from brief sparks and careful mathematics rather than traditional pictures. Cosmic ray detectors placed on balloons, satellites, and ground arrays record charged particles that constantly rain onto Earth. Each particle leaves tracks, ionization trails, or bursts of light in detection media. By measuring directions, energies, and composition, scientists infer the astrophysical accelerators that launched them, but the journey through space, the fields crossed, shocks encountered, and interactions suffered, remains unseen, reconstructed only from these tiny signals collected at the end of the voyage. Exoplanet hunters often discover new worlds by watching a star gently dim as a planet passes in front of it. These transits reduce the star's brightness by fractions of a percent, far too subtle for the eye. From repeated dips, astronomers calculate planet sizes, orbits, and sometimes atmospheres, even though no image ever shows the planet itself. The discovery rests entirely on the quiet rhythm of light curves recorded over time.
Another method, radial velocity detection, measures how stars wobble due to unseen planets tugging on them. Spectrographs detect minute shifts in stellar spectral lines caused by Doppler motion, sometimes only a few meters per second. From these shifts, astronomers infer planet masses and orbits without ever seeing the planets. The signature lies hidden inside starlight, extracted by precision instruments acting like cosmic seismographs. Interferomotors link multiple telescopes to act as one, combining light waves to reveal details impossible for a single instrument. The targets themselves may never appear clearly. Instead, scientists interpret interference fringes that encode spatial information. By mathematically reconstructing patterns, they unveil fine structures within stars, disks, and jets. The object is never directly seen at high resolution, only revealed through delicate patterns created when waves blend and cancel. Spectroscopy breaks light into wavelengths, showing absorption and emission lines that reveal composition, temperature, motion, and pressure. Instead of seeing atoms or molecules directly, astronomers analyze the fingerprints they leave in starlight and nebula glow. Each line tells a story about the conditions in remote environments. The universe, in this way, is decoded not by images, but by patterns inscribed within light itself. Polarization measurements reveal how light has interacted with dust, gas, or magnetic fields. Telescopes measure not only brightness, but the orientation of electric fields, detecting subtle alignments across the sky. From these signatures, scientists infer the presence of interstellar grains, scattering processes, and ordered magnetic structures. The dust and fields remain invisible, only the way they alter light exposes their presence. Gravitational microlensing occurs when a compact object passes in front of a distant star, temporarily magnifying its brightness through gravity alone. Observers see no image of the lensing object, only a smooth brightening and fading of the background star. From the shape and duration of the event, they deduce mass and sometimes the presence of unseen planets. This technique reveals wandering worlds and faint objects that emit little or no light. Time delay measurements in strong gravitational lensing systems allow astronomers to probe cosmic expansion and mass distributions.
Multiple images of a background quasar flicker at different times as light travels along paths of varying length. By measuring these delays precisely, scientists infer the geometry of space-time and the mass of intervening structures. Nothing new appears visually, only recurring echoes of the same object, yet the delays carry deep cosmological information. Fast radio bursts are short, intense pulses that last only milliseconds, traveling across billions of light-years. Instruments capture their arrival times at different frequencies, revealing how much ionized material they passed through. From each dispersed pulse, astronomers map invisible plasma between galaxies and track otherwise hidden matter. These bursts act like cosmic probes, lighting up material that leaves almost no other trace. Laboratory astrophysics recreates space conditions using lasers, plasma devices, cryogenic chambers, and particle accelerators. Scientists simulate shocks, magnetic reconnection, molecular formation, and radiation fields under controlled circumstances. The experiments do not show the cosmos itself, but they validate models describing unseen processes occurring light-years away. Carefully measured data then feed back into theories that interpret observations of things no telescope can directly witness. Precision clocks on satellites and Earth test general relativity by measuring gravitational redshift and time dilation. No one sees space-time bending, but clocks tick differently, in strong gravitational fields confirming predictions. By comparing frequencies, scientists probe the invisible curvature around planets and stars. Time itself becomes the detector, quietly recording the shape of gravity. Underground, underwater, and under ice detectors search for exotic particles like axions, dark photons, and other hypothetical components of hidden sectors. These experiments look for tiny energy deposits, resonant signals, or unusual conversions of particles into light, or vice versa. Most runs yield null results, tightening constraints and narrowing the search. The quest is guided by faint possibilities, where discovery would emerge not from brilliant images, but from a quiet, unmistakable signal rising above background noise. Human eyes evolved to respond only to a narrow slice of the electromagnetic spectrum, leaving most cosmic radiation completely invisible. Infrared, ultraviolet, X-rays, gamma rays, and radio waves pass unnoticed unless instruments convert them into colors or sounds we can perceive. What we think of as the night sky is therefore only a tiny fragment of reality. Our biology filters the universe, allowing us to see beauty while hiding the vast majority of what exists. The human brain interprets light as shapes, motion, and color, yet it cannot perceive gravitational curvature, magnetic fields, or space-time distortions directly. We feel none of the bending of light around massive objects, none of the stretching caused by gravitational waves. Instead, mathematics, instruments, and models translate these effects into visualizations. Our nervous system gives us a comfortable world, while the true physical world remains largely beyond our senses. Many animals experience aspects of the universe humans cannot detect without technology. Birds perceive Earth's magnetic field and use it for navigation, perhaps through quantum effects in their eyes. Bees see ultraviolet patterns on flowers that guide their feeding. These sensory worlds exist parallel to ours, revealing that biology samples only selective pieces of reality. The cosmos contains signals everywhere, but each species perceives only part of the total message. In deep time, cosmic radiation has subtly influenced biological evolution. Supernova particles, solar storms, and background radiation occasionally alter DNA, contributing to mutation rates. Life adapts and changes without ever seeing the forces shaping its inheritance. The interaction between cosmic processes and biology unfolds quietly over millions of years, recorded only in genetic histories and fossil transitions, not in visible cosmic scenes. Inside the human body, natural radioactivity from potassium, carbon, and other elements constantly produces tiny bursts of energy. We never sense them. These quiet events are remnants of stellar processes that forged the atoms making up our tissues. Every heartbeat, every breath takes place amid a subtle background of radiation, linking us directly to cosmic origins in ways our senses cannot detect. Astronauts orbiting Earth sometimes experience brief flashes of light, even with their eyes closed. These are caused by high-energy particles passing through the retina or visual cortex, triggering phantom perceptions. The flashes do not correspond to external light, yet they remind travelers that space is filled with invisible radiation. Human perception becomes a delicate interface between biology and cosmic particles, moving quietly through the body. In the absence of gravity, the body's internal senses must adjust, because balance and orientation rely partly on fluid shifts and pressure cues. Astronauts do not see gravity, but they feel its absence in dizziness, disorientation, and muscle changes. Over time, the nervous system recalibrates to a new baseline, proving that our bodies evolved for one gravitational environment, while the universe contains many. Circadian rhythms respond to cycles of light and darkness, but cosmic influences like seasonal sunlight variation and night sky brightness changes subtly shape human sleep and mood patterns. Our internal clocks sync to environmental cues without detecting stars or space itself. The connection is indirect, carried through hormones like melatonin and neural timing circuits. The body responds to astronomical rhythms while remaining unaware of their cosmic origins. Plants sense gravity through cellular structures called statoliths, which settle under their own weight and direct growth downward or upward. They never see gravity, they simply respond mechanically to its pull. This quiet biological dialogue with an invisible force shapes forests, fields, and entire ecosystems. Every tree trunk and root system reflects a silent conversation between life and unseen physics. Marine organisms that migrate vertically through oceans often time their movements with lunar cycles. They do not observe the moon's orbit consciously, yet gravitational tides set patterns for feeding and reproduction. Vast biological migrations unfold according to rhythms linked to celestial mechanics. The organisms themselves experience only subtle environmental cues, unaware of the cosmic choreography directing them. On Earth's surface, atmospheric shielding protects life from most cosmic radiation, while the magnetosphere guides charged particles toward the poles. Humans never perceive these protective layers directly. We walk beneath an invisible shield shaped by planetary physics, one that makes conditions for life possible. Without it, the biosphere would face constant exposure to harsh radiation pouring from space. Migratory animals such as salmon, turtles, and birds possibly combine chemical, magnetic, and celestial cues to navigate over immense distances. Some detect tiny differences in the angle of starlight or the polarization of the sky. Others rely on geomagnetic signatures embedded in memory. Their journeys reveal biological sensitivity to environmental traces of cosmic phenomena that remain invisible to the human eye. The human visual experience of the night sky is filtered further by the atmosphere. Scattering, refraction, and absorption change colors and soften stars, often hiding faint structures. We never see the true brightness or positions of celestial objects directly, only their altered appearances after traveling through layers of air. Our senses provide a comforting illusion rather than a literal view of the universe. Sound does not travel through space, yet we often imagine cosmic events as loud and dramatic. In reality, explosions, collisions, and stellar births unfold in silence. Instruments convert electromagnetic and particle data into audio for analysis, but the original events are quiet. Biology expects sound where there is none, reminding us that our senses evolved for Earth, not for the vacuum beyond it. Radiation sickness results when high doses of energetic particles damage cells faster than the body can repair them. The radiation itself is invisible, odorless, and silent, but its effects unfold deeply within tissues, Symptoms arise only after biological systems respond to the accumulated harm. This disconnect between unseen cause and very real consequence highlights how limited our direct perception of cosmic hazards truly is. The brain constructs color from wavelengths, but there is no intrinsic blue or red in light itself. Colors exist as neural interpretations. When astronomers assign false colors to infrared or X-ray images, they extend our senses artificially, transforming non-visible wavelengths into something the brain can understand. These images look natural, yet they are translations of signals no human eye could see unaided. Even gravity, the most constant force we experience, reveals itself only through weight and motion. We do not sense gravitational fields as such, we experience only their effects on our bodies and surroundings. The curvature of spacetime that drives planetary orbits remains conceptually hidden. Biology evolved to handle practical consequences rather than to comprehend the underlying structure. Psychologically, the night sky evokes awe, calm, or existential reflection, not because we perceive the true universe, but because we encounter symbols of distance and time our minds can barely hold. This emotional response shapes art, religion, and philosophy. The cosmos influences human culture through feelings rather than direct sensory knowledge. Our inner lives expand in response to something largely unseen. The chemistry of life itself depends on stellar nucleosynthesis. Carbon, oxygen, nitrogen, iron, and many other elements were forged inside stars and supernovae. No living system witnessed the reactions that created its atoms. Biology simply inherited the results. Every cell, every protein, every breath arises from long-past cosmic processes invisible to anyone who now exists.
Finally, human exploration of the universe relies entirely on instruments extending our senses. Detectors, spectrographs, antennae, telescopes, and probes. None of them show reality as it looks. They translate invisible signals into images, graphs, and sounds. Our entire understanding of the cosmos is built on mediators that bridge biology and physics. Through them, we learn to imagine what our senses alone could never reveal. Galaxies slowly change shape over billions of years, transitioning from chaotic irregular systems into spirals, and then sometimes into smooth ellipticals. The changes happen through mergers, gradual accretion, and internal processes that redistribute stars. None of this is visible on human timescales. Every image we see is a frozen moment in an ongoing transformation. Only by comparing populations across cosmic distances can astronomers reconstruct the slow story hidden beneath static snapshots of the night sky. Spiral arms in galaxies are not solid structures, but patterns that persist as stars move in and out of them. Individual stars orbit at their own speeds, while density waves travel through the disk, compressing gas and triggering star formation as they pass. Over millions of years, different stars light up different parts of the arms, giving the illusion of permanence. The spiral pattern endures, even though the material constantly cycles through. Stars themselves evolve so gradually that no telescope ever witnesses the changes directly. Their cores contract, their outer envelopes expand, and their luminosities shift over millions to billions of years. Models and stellar clusters reveal the sequence, but the transformation is inferred, never observed in motion. Each star we see is simply paused at one stage of a lifelong process that unfolds far too slowly for human perception. Planetary orbits drift subtly over long periods due to gravitational interactions and tidal forces. Over millions of years, small perturbations accumulate, shifting eccentricities, inclinations, and resonances. The solar system appears stable to us, yet its architecture is constantly evolving at a pace invisible to any single lifetime. Simulations reveal chaotic sensitivity that quietly reshapes trajectories across deep time without ever producing sudden visible drama. Tidal friction gradually transfers angular momentum between rotating bodies and their satellites, altering both spin and orbital distance. Earth's rotation slows, days lengthen,
and the moon drifts away by centimeters each year. No one notices the change directly. Clocks and measurements reveal it only through careful comparison. Over geologic spans, oceans, continents and climates all respond to this quiet, relentless adjustment. Continental drift on Earth carries mountains, oceans, and ecosystems across the planet's surface. Plates move only centimeters per year, too slowly for the eye to detect. Yet over tens and hundreds of millions of years, entire landscapes rise and disappear. Life adapts to new climates and coastlines shaped by tectonic forces that never announce themselves in real time. Planetary atmospheres evolve slowly due to volcanic outgassing, chemical reactions, escape to space, and interactions with the solar wind. Carbon dioxide cycles, oxygen accumulates, methane rises and falls, all over millions of years. Observers today see only an instant of this ongoing transformation. The layered histories lie encoded in rocks, ice, and isotopes rather than in anything visible happening in the sky. Stars in galaxies gradually settle into new distributions under the influence of gravity. Collisions between stars are rare, but gravitational tugs add up, redistributing energy over long timescales. This process, called relaxation, smooths out clumps and structures without leaving obvious signs moment to moment. The galaxy becomes more orderly through interactions no one ever sees occurring directly. Globular clusters evolve as heavy stars sink toward their centers, and lighter stars drift outward. Over time, evaporation slowly removes stars entirely, sending them into the galaxy. The cluster retains its spherical appearance, hiding internal rearrangements taking place star by star. Only detailed modeling and long comparisons reveal the silent reshaping underway. In galaxy clusters, hot gas cools very slowly, radiating energy and drifting inward toward central galaxies. Feedback from black holes prevents catastrophic collapse, reheating the gas periodically. The balance between cooling and heating unfolds over billions of years. Observers glimpse only snapshots of a long dialogue between gravity, radiation, and invisible energy flows. Black holes grow through accretion and mergers over cosmic timescales. Most of the time they consume matter quietly, without dramatic flares. Their masses increase bit by bit, altering surrounding orbits and gravitational fields. No visible sign shows the long accumulation, yet by the time we measure them, they have silently recorded entire histories of growth. White dwarfs cool for billions of years, fading gradually into colder and dimmer remnants. Without nuclear fusion, they radiate stored heat extremely slowly. Eventually, they will become nearly invisible black dwarfs, theoretical objects not yet seen because the universe is too young. The journey from bright ember to darkness happens in silence, far beyond human observational timescales. Neutron stars spin down over time as they radiate energy, gradually slowing their rotation and weakening their magnetic fields. The process can take millions of years, gradually transforming pulsars from rapid flickering beacons into quiet, undetectable remnants. Each lost bit of rotational energy is imperceptible moment by moment, but cumulative across ages. Cosmic rays wandering through the galaxy follow tangled magnetic field lines and scatter repeatedly, taking millions of years to travel distances that light crosses in days. Their paths are twisted and indirect, impossible to reconstruct exactly. When one finally reaches Earth, it represents the end of a journey so long and complicated that the history is forever hidden. Only the arrival is known, not the story. Dust grains wandering between stars gradually erode through collisions, sputtering and radiation. They slowly change composition, size, and shape. Over long intervals, grains become seeds for molecular formation, clouds, and future planetary systems. What begins as a tiny particle slowly participates in cycles spanning billions of years without ever being noticed individually.
Galactic bars, elongated stellar structures across spiral galaxies, grow and dissolve over time as gravity redistributes angular momentum. They funnel gas inward, trigger star formation,
and reshape the central regions of galaxies. Eventually, they may weaken or vanish, replaced by other structures. The rise and fall of bars occurs too slowly for any observer to watch directly. Large-scale cosmic filaments thicken gradually as matter streams along them toward nodes and clusters. Gas heats, dark matter accumulates, and galaxies migrate slowly toward denser regions. The web appears static in any image, but it is continually evolving. Over billions of years, the structure becomes stronger and clearer, shaped by gravitational attraction that operates quietly and persistently. The cosmic abundance of elements changes little by little as new stars forge heavier nuclei and then return them to space. Each generation contributes microscopic adjustments to the chemical balance of the universe. Over time, regions become richer in metals, enabling rocky planets and complex molecules. The enrichment proceeds invisibly across aeons, recorded only in spectra and stellar populations. Even the expansion of the universe reveals its true character only through long accumulation. Galaxies drift apart gradually, the scale factor increasing fraction by fraction. Human lifetimes see no noticeable difference. Yet across billions of years, the separation becomes immense, driven by energy we cannot see, and measured through light from distant pasts. Far beyond the places where telescopes can gather faint light, there are regions of intergalactic space, so empty that a single atom may drift for centuries before meeting another. Nothing dramatic happens there. Temperature hovers just above absolute zero, and the slow expansion of the universe gently stretches distances. These quiet voids exist as serene intervals between structures, reminders that most of the cosmos is not filled with events, but with stillness. As galaxies move farther apart with cosmic expansion, more and more of the universe slips beyond our observable horizon. Light traveling toward us can no longer bridge the growing gulf, leaving entire regions eternally unseen. Nothing signals their departure. They simply fade from possibility, becoming part of a realm we know exists but will never witness. The boundary is not a wall, only distance expanding into silence. Within galaxies, vast clouds of dark matter cradle stars and planets without ever announcing their presence. They extend like gentle, transparent tides, shaping orbits and guiding motion through gravity alone. No glow reveals their outlines. They are felt, not seen, providing a quiet framework upon which the bright parts of the cosmos rest, like lanterns hung on invisible beams. In the long future, star formation will slow as gas becomes locked into existing stars or expelled into space. The night skies of distant civilizations would gradually grow emptier, with fewer newborn suns lighting their galaxies. The process unfolds softly, like a fire burning low. The universe, once filled with star birth, drifts toward a calmer, more subdued rhythm. Black holes that now seem fierce are mostly quiescent for most of their lives, sitting quietly at the centers of galaxies, influencing everything through gravity alone. Their horizons hide events from the outside world, and yet most days, nothing dramatic crosses them. Over unimaginable spans of time, they will slowly lose mass through Hawking radiation. The transformation occurs too gently for any observer to notice moment by moment. White dwarfs cooling in the darkness emit weaker and weaker light until they become nearly undetectable. Their glow fades gradually, like embers sinking into ash. No flash marks the end. They simply merge with the night, still embodying the history of the stars they once were, but offering almost no signal to reveal their presence. Cosmic background radiation, once brilliant, has stretched and cooled as space expanded, becoming a faint microwave whisper that fills the sky. It now bathes the universe in a uniform chill, barely above absolute zero. Over cosmic time, it will fade still further, sliding beyond wavelengths any instrument can realistically detect. The last echo of the Big Bang will become a lingering murmur, dissolving into darkness. Gravity binds galaxies into clusters that drift together through space, circling their shared center of mass. The dance is slow and quiet, lasting billions of years. From afar, nothing appears to change. Only the gradual tightening of orbits and the subtle accumulation of mass mark the passage of time, a graceful movement hidden beneath apparent stillness. Stars traveling in galactic halos move through vast arcs around the center, sometimes taking hundreds of millions of years to complete a single orbit. To human eyes, their positions barely shift over lifetimes. Each remains fixed in the sky, yet all are slowly, silently migrating along trajectories carved by gravity. The sky is a moving tapestry that moves too gently to see. Light traveling through space gradually stretches into longer wavelengths as the universe expands. Photons that begin as bright visible colors drift toward red, then infrared, then radio. Eventually, they become so stretched that they fade into the fabric of the cosmos itself. No abrupt transition occurs. Energy simply softens, dispersing quietly across space. The faint glow of intergalactic gas exists at densities that approach emptiness. It absorbs and emits light so feebly that only sensitive instruments can detect its presence. Yet this thin material threads the universe together, connecting galaxies across cosmic webs. Its calm existence reflects the fact that not all structures blaze. Some remain in gentle equilibrium for eons. Dark energy continues to shape cosmic destiny without ever appearing as an object or signal. It does not sparkle, ripple, or gather. It whispers into space-time, encouraging expansion to accelerate. It is everywhere and nowhere, a quiet influence that guides the universe forward without ever becoming visible in its own right. Faint dwarf galaxies orbit larger ones like unnoticed companions. They hold few stars, making little light. Many slip past without drawing attention, gradually influenced by tides and interactions. Over time, they dissolve into stellar streams that gently wrap around their hosts. Their histories live on only as soft traces woven into larger structures. Shockwaves from ancient supernovae continue to expand into interstellar space long after their brilliant explosions have faded. The fronts move outward slowly, thinning into near invisibility. What was once violent becomes delicate. The universe absorbs the disturbance, leaving only a subtle imprint in gas and dust that drifts into new formations. In quiet corners of planetary systems, comets and icy bodies orbit far from their stars, disturbed only rarely. For most of cosmic time, nothing happens to them. They drift in cold storage, preserving records of early formation. Their stillness is part of the cosmos too, a patient waiting that can last longer than life on worlds nearer the light. On worlds with atmospheres, slow chemical cycles reshape climates across epochs. Carbon moves from rock to air to ocean and back again, with no visible drama. These changes are so gradual that generations live and die without noticing. Only long views reveal the steady, thoughtful pace of planetary change. Deep-time geological processes lift and lower mountains, open oceans, and erase scars. The planet's surface seems permanent, yet every landscape shifts. Each grain of sand participates quietly, carried by wind, water, or gravity, forming patterns that feel timeless but are always in transition. In the far future, only faint remnants of galaxies may remain visible to any surviving observers. Local groups will merge, while distant structures recede beyond reach. The universe becomes more isolated, more inward, shaped by small pockets of gravity against a backdrop growing darker. Change continues, but in softer, slower tones. Entropy ensures that energy gradually spreads, structures diffuse, and orderly systems relax into equilibrium. This is not destruction in any violent sense, simply the easing of tension, the settling of differences. Over cosmic spans, heat disperses, contrasts fade, and the universe drifts into quieter states. It is a long exhale, written into the laws of nature. Eventually, whatever remains, faint stars, cooled remnants, drifting particles, will continue along their paths in vast calm darkness. No final moment announces itself. Instead, the cosmos grows quieter, more spacious, and more still, carrying the memory of all that once burned and shone. In that quiet, everything simply continues. And now, let the thoughts soften, and the universe feel wide and gentle around you, vast, patient and calm, needing nothing and asking nothing at all.